now we will continue the topics discussed last seminar. So last seminar we have discussed linear differential equations, but today we will discuss non-linear differential equations. We will try to find critical points and linearize our systems near critical points, and discuss the nature of these critical points, stability, phase portraits, and so on, locally near critical points of non-linear differential equations. Okay, so this is seminar 11, and we will discuss stability. Well, and so the task is, so this is the general task for all the problems to be discussed. Determine all critical points of the given system of equations. Find the corresponding linear system near each critical point. So find the eigenvalues of each linear system. What conclusion can you then draw about the nonlinear system? Draw a phase portrait of the nonlinear system to confirm your conclusion, and so on. Well, so and to analyze this, and we will start with the first system, which is x prime equals 4 minus 2y, y prime equals 12 minus 3x squared. Oh, but sorry, I have forgotten to discuss the, during the lecture, I have forgotten to discuss the linear system describing the oscillating pendulum, the linearization of the system describing the oscillating pendulum. Maybe it is important, maybe I will write only the answer, so it is not difficult to obtain how to linearize the system, right? So I will start with them. So for pendulum, we have obtained the following system: x prime equals y, and y prime equals minus gamma y minus omega squared sine x. Okay, and 0, 0 is an equilibrium, and to linearize this system, we must find the Jacobian matrix. Right? So we will write them. So the first row consists of partial derivatives of this term with respect to x and y, right? So it will be 0 and 1. Next, take the first derivatives of this function at the point 0, 0. It will be minus omega squared cos x and minus gamma. But if we substitute x equals 0, the origin, we will get the following matrix: 0, 1, minus omega squared minus gamma. And so this system can be rewritten as, x, y prime equals this matrix 0, 1, minus omega squared minus gamma multiplied by xy plus what? So plus 0, 0, and minus omega squared multiplied by sine x minus x. So this is a times x plus g of x, right? G of x is some, so it is a small function in comparison with displacement x, with the vector x. So now this is small with respect to x, of course. If you know, so if we discuss exactly this function g, Now, is it clear that this is small in comparison, so in comparison to x? Why is it small? Because sine x minus x is equal to, using Taylor expansion, it is equal to minus x cubed over 6 plus of x to 4. And if we now divide this difference by x, the quotient will approach 0, right? So you're absolutely right that the system may be linearized near the equilibrium position, near the equilibrium. Sine x can be replaced by x, and we can then analyze the phase portrait of this linear system, and qualitative analysis will give the same result as for this non-linear original system, right? So usually we analyze linearized system for a pendulum. So the same situation is true. So it's hold for this system. It is not linear, non-linear, right? Because we have x squared here, right? And the analysis of this system consists of several steps. So step number 1 is to find critical points of equilibrium. To do this, we should solve this system of equations, simultaneous equations, from which we have y equals 2 and x is plus or minus 2. So we have 2 points, maybe P1, which will be 2, 2, and P2, which is negative 2, 2. These are 2 critical points. So this is step number 1. Step number 2, we will try to linearize system near each of these critical points. What shall we do? So we know how to linearize the system near the origin. So if the origin is a critical point, then we can replace f of x by the Jacobian matrix. So multiplication by the Jacobian matrix. A is the Jacobian matrix. Right. So, but P1 is not an origin. So we should first make a change of variables that translate this point to the origin. So we will introduce new variables. Okay, so u will be equal to x minus 2, or x equals u plus 2. And v, which is equal to y minus 2, which is the same as y equals v plus 2. And then we should rewrite our system in terms of new variables u and v. Okay, is it clear, Daniel? Is it clear? Yeah. So what shall we do now? Daniel, do you know? Make a substitution and rewrite our system in terms of new variables u and v. So if we substitute u plus 2 for x, we will get, so the derivative of x is the same as the derivative of u, right? So we should write u prime equals 4 minus 2y, but y is v plus 2, so 4 minus 2 times v plus 2, and y prime is the same as v prime, which is 12 minus 3 times u plus 2 squared. Now we need to simplify this, right? So now, is it clear? So to rewrite this system in this form. Next, to simplify. And we will get the following. U prime equals, so if we simplify, we will get minus 2v without constant term, right? We have no constant term now. And v prime equals, so it is 12 minus 3u squared minus 12u and minus 12. Cancel out by cancelling out the same terms. We will get minus 12u minus 3u squared. Okay, is it clear? Well, and now we're trying to find the linearized system. So this system is not linear, but what is the linearized system? So we should replace this by the Jacobian matrix multiplication. So it must be, so it's step number 3. uv prime is equal to, so we must write the Jacobian matrix. Okay, so this matrix, so the coefficients of the first row is 0, minus 2. So it is clear because the Jacobian matrix coincides with. So this is the linear part, and so we can rewrite it. And also here we have this linear part and the Jacobian. So the Jacobian matrix will be the derivative with respect to u is minus 12 and minus, and this is 0 at the origin, this part. So so df2 over du is equal to minus 12 minus 4u generally. But at the point u equals 0, it will equal to minus 12, right? So minus 6u, thank you, minus 6u. So it will be minus 12 and 0. And plus, so 0 and minus 3u squared. But this will approach, so this will be the part, this will be the function g, which is small in comparison with x, but we will not, so we need not check this. Because by theorem, so if these functions are twice are of class C2, then it is automatically small with respect to x. Right? We may use the definition of the differential function, right? The function, the derivative of the function, the differential.
What is u equals to x minus 2 and b equals to y minus 2?
Sorry.
So the second, I don't understand for the second part. Why does u equals to x minus 2?
This is a substitution. So by definition.
But for what do we substitute for?
Because we need to move this critical point to the origin, because this theory was constructed for the critical point at the origin, but our critical point is not the origin, so we must make a change of variables, right, to move this point to the origin. So now by this substitution, the coordinates u and v of this point are 0 and 0, so this is moved to the origin.
How about P2? Because P2 is minus 2 and 2.
And we will analyze this separately, right? So we will first complete the analysis of this at the point P1, right? So for P1, this is only made for the point P1. We will make the analysis for the point P1. We will complete it, and after this, we will analyze our system near the point P2. So we will do the same. So we will start with a change of variables, and then. Right. So our goal is to analyze this. Okay, so our matrix is 0, minus 2, minus 12, 0. The characteristic equation will be minus lambda, minus 2, minus 12, minus lambda. Lambda squared plus 24 equals 0. Okay. Minus. Sorry, just minus. Right. Minus 24. Why minus? So minus and minus. So plus. Right. So now lambda is equal to plus or minus root 24 or plus or minus 2 or 6. And now we are trying to find the eigenvectors. For lambda 1, we substitute 2 root 6 for lambda 1, and we will get the following matrix: minus 2 root 6 minus 2 minus 12 minus 2 root 6. And the eigenvector is v1, which is equal to, so it will be 1 minus root 6, right? So it is easy to guess. And lambda 2 is minus 2 root 6. And we will get, so we need only the first row. It will be 2 root 6 and minus 2. And the vector will be, the eigenvector will be 1 and root 6. Right, so 2 eigenvectors. And the phase portrait. So we have a point. Now the point P1 is 2, 2. So 2 and 2. And this is a critical point. These are 2 eigenvectors, 1 and, so this is minus and minus, so it's this direction, and 1 root 6 is this direction. Not through the point 1, something like this. Okay. Well, if we approach this point from the direction determined by V2, we will approach our equilibrium, and this way. So we have the phase portrait, which looks like this, right? This is a saddle point. Okay, and it is unstable. It is unstable, right? This critical point is unstable because if we so there is no any neighborhood of this critical point such that if we start from the point in this neighborhood, we will remain in this within this circle, right? Because, for example, if we can see the points on the line determined by these vectors, for example, if we start from this point, we will remain on this straight line, but we will go away from this critical point, so it is unstable. And by theorem, it will remain unstable even for the original system, right? It will remain unstable because we have lambda 1, which is greater than 0. By theorem 2, if we have lambda with this property, with positive real part, then this point will be unstable even for the non-linear, for the original system, non-linear, right? Well, now let's analyze the second point. So step number, not 2, it is step number 4. We must consider P2, negative 2 and 2. Welcome. Right, so first change of variables. change of variables. Maybe it's better to rewrite system on this part of the board. So x prime is equal to 4 minus 2y. X prime is 4 minus 2y, and y prime is 12y minus 12 minus 3x squared. 3x squared. And we will try to draw, to sketch the figure for this case also. So this will be the second point. So this is the first point, the second point. Plus, not plus 6, but well, plus 12, I think, 12. So multiplied by twice, 2 times u. Right. 12. And that's all. Minus 12 and plus 12. And it is cancelled out. Well, correct.
Now we need to make, what's the name of the Johnson matrix?
Jacobian. Okay. Did you discuss this matrix in calculus, Jacobian matrix, or maybe how Pankratov called this matrix? Jacobian. So the matrix of the partial derivatives of partial derivatives. No? Yes. So it must be studied in calculus. No. No, it must be studied in calculus when the so differentiability of functions of several variables is discussed. Differentiability, so theory, Jacobian matrix.
Nabla operator?
Nabla on. Nabla is for the function when we have a scale of function depending on several variables, right? So the gradient is Nabla, yes, is the Nabla operation. But if we have several functions, right, vector function depending on several variables, we must speak about the Jacobian matrix, the matrix of partial derivatives.
Jacobian also in thermodynamics or Maxwell's transformation. Как вы получили U плюс U tag 4 minus 2 U plus 2?
How to obtain what? Minus 2v?
Вот как мы до сюда дошли?
Just substitution. So we have written change of variables, and next we are trying to substitute this change of variables here. So if we take the derivative of x, it is the same as the derivative of u, right? So I have replaced the derivative of x by the derivative of u, because x prime is the same as u prime. So from this substitution, right?
Okay.
And next y is replaced by this v plus 2. So v plus 2 is substituted for y.
And then we different.
Right. So only simplification. So
Yeah,
cancel
so
out
simplify
similar. Right.
and then
Simplify.
differentiation and
Right.
then
Right.
calculate. Okay.
And take only linear terms or using the Jacobian matrix. Complex number. So we need not know v because we know that in this case we have a center. So if the eigenvalues are purely imaginary, then we need not know the vectors because we can't draw these vectors in the real plane. They will be complex, right? But we know the classification in this case. So the classification suggests that we have the type of center, right? Circles.
The spiral?
So it is not the spiral thing because they are purely imaginary. So purely imaginary. If they have some real part, then we have a spiral sink or spiral source. But in this case, we have a center, right? The center, and so the figure. Now the figure will be this. We may only we want to, if we want to determine the direction of rotation, we need to take some point. Maybe let it be for example, thank you, follow. Let's consider a point, maybe -1, 2. And see the direction of the tangent vector, right? At the point -1, so the point is -1, 2. We must substitute this point. I will write here, write it here. This is needed to determine the direction of rotation, counterclockwise, clockwise.
Can we choose a random point?
Yes, the random point, but it is convenient to take this point because so it is easy to determine the direction. So at this point we have the vector, which is, let's substitute it here, so we will get 0. The first component is 0 and only the sign of this, so it is 9. So the tangent vector is this, and so the rotation is counterclockwise. And so this is the direction of the rotation around this these orbits. Okay, so we have done qualitative analysis of this nonlinear system. Locally, it looks like this pattern, right? It resembles this pattern and this pattern. But globally, it is impossible, of course, do this having only the analysis, local analysis. But if we use some computer device and some graphing device to plot these graphs, you will see something like this. So I saw the global phase portrait. It looks like this, and then the trajectories go that way. Okay, so this trajectory goes this way, yes, then this way, right? Something like this. So this is the global phase portrait, but I'm not asking to draw the global phase portrait. We want to analyze these systems locally, but you should know that all these parts can be gathered together and they can be used as bricks to construct the global phase portrait. But it can be done only maybe using the computer device, right? Some calculating devices, right? Okay, so this is the answer. Let's continue. Let's look at the. So first find critical points, then move each of the point to the origin, linearize the system near the origin, and find critical points. Not in mind, yes. So equate the right-hand parts to 0 and try to find critical points first. Okay. -2 and 1, yes, exactly, and find y. Okay, substitute. Y cannot be imaginary, of course, right? Yes. And so you need only.
So we'll just do
Right. Yes. Only one x can be equal to 1, and then y is plus or minus 1. So very easy. And so we have 2 critical points. 1, 1.
Okay, transformation.
U
is equal to I want it to be 0 at x. So when x is equal to 1, we should be 0. So
just subtract this critical coordinates. Yes, yes, correct.
so P1
V
v minus 1
and
and now
y minus 1. Y minus y. It must be y.
okay, now
Correct. Simplify then.
so can I already write it as it?
Yes, yes, it's possible.
So it will be
So the constant terms must be cancelled out, as you as you see before, as you saw before. Well. So not multiplied by u and v. So it is not the matrix. So this is the equation in the matrix form. It's okay. And now you should take on the linear parts for the matrix for the linear term, and right. So you should gather all these linear terms together, and squared terms will give us g, which is 0, right? Which can be.
So we should. I'll already write the
You can
Jacobian
neglect this, right.
So I'll just write 1 minus 2. I'll write the Jacobian.
Or you may do it. So you need not write the Jacobian matrix. So now it is clear that all the linear terms can be gathered into the matrix, and we can neglect, right, their square terms, right? They're small in comparison with the norm of u and v. So this is the linear part, squares, and the quadratic part. In this case, it is clear, but if we have some other functions, arcsine or logarithmic function, so we will consider this case.
We can just write it by without writing the Jacobian explicitly.
Okay.
Am I right?
The Jacobian. So I think you needn't do this, right?
So
yeah, I think it is clear.
Polynomial, we can directly.
Right. In the case of if this is polynomial, right, it is clear, of course.
Okay, now should I find out the eigenvalues now?
Right. Now eigenvalues, yes, eigenvalues, eigenvectors, if we need them. Plus 4, correct.
Okay, 6, 2, 3, 6.
I think
It to solve the quadratic?
I think it's complex. It's a complex. It will be complex.
The roots will be complex b squared.
I think
minus,
yes.
9.
So 3 plus or minus 9 minus. Okay. So this is not easy, but we need not find the eigenvectors in this case, because we need not know complex eigenvectors, right? So from this result, we can conclude that we have, so if lambda is complex, we have one of 3 cases. So it may be spiral source, spiral sink, or a center point, center, yes, center when it is purely imaginary, but now it is, so it is unstable point, and so it is source, right? So since the real part is greater than 0, then we have a source. So it looks like this. Or maybe the rotation may be in the different direction, opposite direction, right? In this direction. And to decide between these 2 cases, we should find the vector, tangent vector, at an arbitrary point near this, right? As before. So we should consider, we have a point 0, 0, yes, 1, 1, for example, and so we should look at this point. So if 1, 1, we should take consider point maybe 1, 0, 0, 1. It's better, right? So do you know, or should I help you?
1, 1. I should draw the diagram.
Yes, but you should determine the direction of rotation. So this way or this way.
To find
so
tangent at 2 points.
Right. Well, you need to know only 1 point. So just 1 point is enough, because you should take any point near 1, 1. So for example, 0, 1 or so 0, 1 is here. So 0, 0 it is here. And to determine the tangent vector. So the original equation.
And y
is minus 1.
Y is equal to also minus 1.
So minus and minus, right? So this way. So the direction is this. So it's something like this. This rotation. The rotation is in this way, right? So spiral source, and rotation of this type.
Okay, now point 2.
And the second point, right?
Substitution is okay.
Like this, but plus 1, y plus 1. You should change the sign, right?
And v is equal to y plus 1. So if we make it plus, the only difference will be in this sign, which will be propagated here, and that will be propagated only here. So only this become changed.
Minus. Yes, minus. It will be minus.
So the matrix is 1 minus 2.
Yes, you're right.
And over here, what will change is
sign of it will be so
Lambda
minus
plus
1.
2 and minus. I'll find it out.
Yes. Lambda minus minus the minus lambda, right?
Plus 4.
Yes, but it is not correct. So let's try to. Is it something wrong? Maybe something else is changed. Why? Maybe so we have so
Yes.
plus here minus 2, right?
Yes. Okay, I'll make the change. So minus
Yes.
2v becomes plus 2v.
And maybe in the preceding case we are not. So something changed. So it is changed here. So if we have y, maybe something's wrong just now. Maybe in the preceding case it was plus 2. Maybe it was plus.
The preceding case is a mistake.
Maybe it may be a mistake.
No, in the preceding
Yes.
case there is no mistake because
In the preceding.
Minus
Okay.
v.
And now we have minus. So let's write plus 1 plus. Yes. Now it is plus. And then 1 minus 2 and yes, plus. Yes, now it is plus, right? Now it is correct. Plus and minus. Well, and now if we change this, we will get so minus 4. Yes, minus 4.
Minus 1, 2. So one of the vectors are 2, 1. And
2 and negative 3. I think it's correct now.
Yes, and the second vector
2, 1. Yes.
4, 2, so 1 minus.
And this is also correct. So the first one corresponds to 2. Yes, 2. Lambda 1 is 2. And lambda 2 is negative 3. And now the phase portrait near the point 1 and negative 1. 1 and negative 1.
Can you help me with the phase portrait?
Yes. So first you should draw the straight lines determined by these vectors 2, 1. So the first vector is 2, 1, but without direction, in order not to confuse with the direction of motion. Yes. So this is V1. 1, negative 2 is this direction. This is V2. And next, if lambda 1 is positive, then we will should move away from the origin along this straight line. So the direction is this, and here the direction is this, and then it will be like this. It's easy.
Okay.
So this is a saddle point. It is unstable, and this is also unstable. Yes. So this is unstable, and that point is also unstable. And saddle point. Thank you. Arcsine of x squared minus 2x minus y. And y prime is ln of 1 minus x minus x squared third. Okay. Okay, welcome. If I'm not mistaken in rewriting this task from the book, I hope so. So first we need to find the critical points.
So now n pi should we consider just 0? All of
Yes. So I think I suggest to solve this first and then substitute in this equation. Yes. So find x. Yes, I think we can find x first. Then x is Okay, well, if x is 0, then y is
y is
just pi n, yes. So x equals 0.
and if it is minus 3 also.
Yes, minus 3.
Just a second. 9 minus 9 plus 6.
9 plus
6, 15. So n pi
15. Y equals pi n.
Y. No, wait, just a second. Well, this is minus.
Minus pi n, yes.
And then 15, so
Minus
15
pi
minus
n, yes. Y equals 15 minus pi n.
15 minus
Pi n. Yes. I think there's no problem with this pi n. I think these critical points so have the same behavior. Yes, because now if we first consider the points of the form 0 and minus pi n and make the change of variables, so u is 0 and v is y plus pi n, then we will get the system u prime equals arcsine. So arcsine u squared or u is x squared minus 2x minus v. So it is not minus v plus pi n, and the second will be v prime equals ln 1 minus x minus x squared over 3 u. It will be u. Am I right? Yes. And u and v. And then arc sine pi n can be rewritten in two ways. If n is odd, so we should consider the case if n is odd and even, and we will only change the sign of arc sine. So there will be two so two types of equations. So if n is 2k, then we can omit, so this will be plus 2 pi k, and the oh sorry, so arc sine, it is not a sine but arc sine. Arc sine, for the arc sine, the argument will must be between 1 and -1.
The answer will be from minus pi by 2 to pi over 2.
And
Flip it by 2
and
pi,
not
it's the same.
and not pi n is not correct. This is correct for sine, but not for arc sine.
Oh, sorry.
It is not this. I think we must change
arc
them.
Sine is arc sine of this is equal to 0, so it is always 0.
Yes, we must equate this to 0 and yes.
So why?
I'll remove this. This is arc sine, and so y is 0 and y is 15 here. Yes. So there are 2 points 0. So 0, 0 and -3 and 15. Oh, sorry, I'm mistaken. So this is my mistake. Plus, and then it is equal to 3. 3, yes.
-3, 3.
-3. So it will be 3, 3, just plus 3 and 3, plus 3, because I have changed the sign. It will be -3, and then plus and 3, yes. Plus 3 and plus 3, yes. And first, let's analyze P1 and how to find the linearized system. And now we need the matrix of partial derivatives, so the Jacobian matrix. The form of the Jacobian matrix is, so I will recall. Do you know how to? Yes. So dx. It must be. So this is, for example, this is f1.
Okay.
This is f2. So partial derivatives. df1 over dx.
dx.
Or du, yes, du. dv. df1. df1 must be f1.
Okay, so I'll calculate the
yes.
Okay, first let me make the transformation. So is it linear? Okay. So u is equal to x. Oh, we don't need transformation for this one.
Yes. We need not do the transformation. So, it's okay.
Yes.
Of working with the same, the same coordinate.
Okay, so partial derivative with respect to x will be
Squared, yes.
And then
so 2x minus 2. Yes, 2x minus 2. And next we must substitute
so
0 and 0 for x and y. And so you may write the matrix and after this substitute the point.
just minus what? Just minus 1.
Minus 1.
And the second part is let me just write everything. And this is the
Yes.
so the Jacobian matrix is minus 2 divided by square root of 1, which is minus 2. And over here it is minus 1. Over here it is minus 1 divided by 1, so minus 1.
Yes.
So a minus I lambda should be equated to 0 for finding the eigenvalues. So minus 2 minus lambda times minus lambda minus 1 equal to 0. So lambda times
Minus 1, yes.
okay, now the
Yes, they're real, and so we need to find the vectors then.
vector. Now I have vectors for plotting them.
So
The real part is negative, so it's a sink. And minus
first draw the straight line through the vectors and through the point 0, 0.
through the
Okay, so first find the vector. It is -1 and the straight line through the origin,
and
right?
through the origin.
This will show the direction. And the next -1 and 1 minus, so it is -1 and
Yes.
here. Yes.
Okay, and now
Yes, and so it is lambda, what is lambda 1 is minus 1 plus root 2, plus root 2, yes? And so it is greater than 0, so it is a source, right? So the direction is away from the origin along this direction, yes? And toward the origin, right? So a saddle point here.
Saddle point means also unstable.
Yes, unstable, yes. And the phase portrait is this. Okay, next, the point 3, 3, and you may use this matrix, but substitute 3, 3 into this matrix. So you need not. So it is. I think it's more difficult to make the shift first, change of variables, and then differentiate. But the matrix will be the same, but you should only substitute this point 3, 3 into this matrix, and you will get the Jacobian matrix. Yes. So substitute 3, 3, and it will be divided by, and this is, so if we substitute 3, 3, we will get, so this is 0. X squared minus 2x is 3 minus 5, so divided by 1. So yes, this is 0. So minus 1 minus 1. Then if we substitute 3, 1, it is also 1 and 1. Yes, 1, 3, right? 1. 1 and 0. This is our matrix.
3 to 6 minus 2, 4. Now the diagram around 3.
Yes.
1 and 2 minus root 3. And this is 1 and 2. Oh, sorry. We have to draw it around 3, 3, right?
Yes, around 3, 3, of course. It's better. Yes, but
go through the
or you may so suppose this is 3, 3. Yes, not to draw it again, or if you if you prefer to draw again through the point 3, 3, of course.
3, 3.
Is here.
So
And then the vector
this and 1 and
minus
something.
my
So
yes,
and
but they are both sources, right? Because these eigenvalues are both positive. Okay, and now how to draw the phase portrait, which is less. So lambda 2 is less. So this is V2 and this is V1. It is less than, and this means that the behavior will be, so they will be tangent to V2.
what is tangent to V2? Okay. These lines.
Yes, yes, near the origin. Yes. So this is nodal source, and the behavior is like this.
So is it stable or unstable?
Unstable, of course. Yes, because they move away from the origin, from the equilibrium point. So unstable. Okay. Well.
Just substitute the forward speed.
Okay. Yes. Yes. I think it's time to stop.